So you have your notes in front of you, all right, and this is something I've typed up for you. I'm going to, same thing, follow it right through. In the beginning, you'd be like, yeah, maybe some of the stuff I don't quite understand, but then in the long run, after we do an example, it'll probably make more sense. Let's walk through this. Chi-square test. There's two different types. There's a chi-square test of good fit, or goodness of fit test, and there's a chi-square test of independence. We are going to focus on the first, on the test of good fit for the first 3 days, and then we'll move into the other one. Okay? And the biggest difference is that it's a 1 by something matrix. That's the biggest difference. So when I look at this, test chi-squared. Chi-squared is a cursive X capital with a little squared, otherwise just called chi-squared, not chi-squared. Is used for comparing 2 or more populations of categorical data. It's goodness of fit. It's a 1 by something matrix. So highlight that, circle that, whatever. Because people are going to go, how do I know which one I should be doing? Well, if it's a 1 by something, it's a goodness of fit. If it's more than a 1 by something, for example, a 2 by 2 or a 3 by 2 or whatever the size of the matrix is, if it's bigger than a 1 by something, it's not a goodness of fit. Then it's going to be a test of independence, which we'll be looking at in a couple of days. Goodness of fit cannot be done on your calculator unless you have a TI-84. If you have a TI-83, you're not going to get a specific p-value. You're going to get an in-between kind of p-value. Okay? Your null. Remember, the null is always the original statement. In the very beginning, you said you thought there would be a difference. If you didn't have that data over there, and you were out in the hallway and you didn't have stats, and I went across the hall to Mr. Hebel's class, and I asked his biology class, and I said, are all birthdays evenly distributed among the 4 quarters? What do you think most people would say? They'd probably say, yeah, they're probably pretty even, right? You have probably evenly distributed. That is the null. I'm not going to change that. That's the original statement. We think it's probably the same for all of them. Okay? The specified distribution of the categorical variable is correct. The alternative is we say it's not correct. We were going to come back and say, I'm not sure. Now you're looking at the data going, no, I think the 4th quarter is too far off. Well, then we have to go through and prove it. Degrees of freedom is number of cells minus 1. Just like linear regression t-test was your count minus 1, this is the number of cells minus 1. That is different. You want to make sure you know that. Because then when we do a line of test of independence, that's going to change. But your number of cells minus 1. Your assumptions, simple random sample. Nothing new there. The second assumption is different. All expected cells greater than 5, or you can't have more than 20% of your cells being less than 5, and you definitely can't have any cells less than 1. If you do, then you have to proceed with caution. Again, all expected cells are greater than 5, and no more than 20% of the cells are less than 5, and nothing can be less than 1. So what's a cell? A cell is quarter 1, there were 19. At quarter 2, there was 28. Quarter 3, there was 16, and then 31. Each one of those is a cell of your original data. And then independence, nothing changes there. Are the events independent? If I'm not quite sure, I might want to do the 10 times n less than the population. So the only thing that's been taken out is the normal part of it, and we're doing the expected cells part, making sure our sample size is big enough in this scenario. Chi-squared is the observed minus the expected squared over the expected, with your expected count being, it depends on the situation. I think I have an equation there. You can cross out the equation for goodness of fit. It's not going to work for goodness of fit. Your expected cells depends on the situation, which you'll see coming up.
Which equation is that?
This part right here, this where it says expected count is equal to row total times column total. Because we don't have rows and columns, we only have 1 row. So you can cross that part out. Expected count is going to depend, and I'll show you that in just a minute. After you find your chi-squared value, take that number and look it up in the chi-squared table. And this is the key part right here. When starting or stating that your conclusion of significance with the p-value, remember to add a description that shows the kind of relationship is present. Remember how with the t-test we went through, and then if you were comparing one to the other, at the very end you'd say at alpha 0.05 I'm going to reject the null in favor of blank, and I think that women go shopping more than men. Remember how we had to add that little sentence, and that was even on our test, and some people missed that part of the test? You really have to do it for chi-squared, because otherwise when you write your conclusion, you're writing a cliffhanger. Because you'll say, we're going to reject the null in favor of this. And people are going to be sitting there going, and what? And you'll see when we get to it in just a minute. Questions on that? Just the generic notes before we do an example? Now, in terms of an example, the book has a good example. You're welcome to write down as I go through when we're doing the quarters born kind of scenario from our data the other day. We'll just see. Okay, which quarter were you born in? My question is, are students' birthdays here at Rosemont High School, are they evenly distributed among the 4 quarters? Okay, so yesterday I had everybody fill in the chart, so I totaled them up. They're all in the circled numbers. Okay, and we're going to be using those for our data over the next couple of weeks. So hopefully that doesn't get, you can see I wrote save all over the place. Let's look at quarter you were born. In the first quarter, we had 19 in our data. In quarter 2, we had 28. Then we had 16. And then we had 31. Right? That's not supposed to be there. For a total of what? 28, 38, 48, 47, 57, 63, 93, 94? For a total of 94. Why is that in our observed data area? State the obvious. Why?
What we observed.
Exactly. You observe it. It's sitting on my board. You observed it. That's my point with having you write that stuff down, is that you can remember, go, oh, well, what did we observe? What did our sample come up with? How about your expected? How do you find your expected count? See if anybody can figure this out. Whoa. Everybody agree? 94 divided by 4. Why 94? That's how many I'm dealing with in this scenario, right? And somehow I have to get a count. Everybody agree that it's going to be a fourth of 94? What's a fourth of 94? Point. I'm sorry, 23.5?
Yeah.
Is that what it was? Sorry, 23.5. What about quarter 2? How many would you expect? 23.5. It should be evenly distributed. That's what we are thinking, right? 23.5. I don't have to worry about the total in that one just because we've got it. Now, the question is, let me go down here. I'll come back. Does it always, do the expected values always have to be the same? And they don't. It all depends on the situation, as I had you write on that sheet of paper. For example, if we go into the sciences and we look at a Punnett Square, big B, little b, big B, right, for whatever they stand for, if you're doing a Punnett Square. This is going to be B, little b. This is little b, this is going to be big B, and this is going to be big B, little b, right? If I just did a Punnett Square. How many, if this is a cross-pollination of a flower, let's just say, how many would I get that's little b? What percent of my flowers that I cross-pollinate would be little b? 25%, right? What percent would be little, or big B? 25. Okay, so I would expect that to be 25%, so I'd be 0.25 times the 94 and 0.25 times the 94, or whatever my sample size is. What about these two combined, though? That would be the 50%. So notice my percents would change in that scenario on the expected value. Depends on what we're dealing with. Okay? I can also talk about we cross-pollinated flowers and we get this type, or corn is one of the things I think they do. They cross-pollinate corn. They're trying to develop this corn that's resistant to different types of weeds. So they go through and they say, well, we have at a ratio 1 to 3 to 8. Whatever it is, whatever the scenario is. That is what they would expect. So how do I convert that into a percent? 8 plus 3 plus 1 is 12, right? So this would be 1/12, this would be 3/12, this would be 8/12. Now I would take 8/12 of whatever my sample size is, I take 3/12 of my sample size. Does that make sense? So it's not always the same like we got here. I just want to make sure people are aware of that. Okay, the null. The 4 quarters will have the same count of the students born. Quarter 1, quarter 2, quarter 3, and quarter 4 are all the same. That's how I wrote this up. Now we're getting into a point where we are writing it out in sentence form. You can't just say mu equals this, or p hat, or p equals this. Chi-squared, your null is going to be in a sentence form, because you're dealing with categorical data. Some people do this, and I would suggest you do this part. You put this in there with it. Q1, Q2, and Q3, and Q4 are all the same. If it was back to the cross-pollination thing, you'd say, I believe the flowers are cross-pollinated in the ratio of 1 to 3 to 7, or whatever it was. And that's why we call it a test of good fit. Does our data fit what it should? Does 19 fit the 23.5? It's a little off, but is it significantly off? Is 28 a good fit to the 23.5? It's off, but is it significantly off? 16 compared to the 23.5. 31 compared to the 23.5. That's why we call it a good fit. Is it match up with what they say it should be? So I should put in here, well, let's just write test of good fit. Chi-squared. Chi-squared test of good fit. Or somewhere in there we should name the test. The alternative is the 4 quarters will not have the same count of students born. That's kind of what I'm wondering. Parameter, are my students' birthdays at RHS divided evenly among the 4 quarters? So I'm specifically looking at students here at Rosemount. Degrees of freedom, how many cells are we dealing with? 8 or 4? I see 8 here. But how many is in our original data? 4. So this is 4 minus 1. So our degrees of freedom is 3. Simple random sample. Let's assume it was a good simple random sample. Okay. Next one. Are all expected cells greater than 5? And are no more than, the reason I have and or is you don't really have to worry about it, just and. If you do have anything that's less than 5, then you have to make sure you fix it, all right? Or we have to go through, we could have 20% or less. Of all cells, and absolutely nothing less than 1. Let's go back up here. All expected cells greater than 5. For my work, I would just go back up here, draw an arrow. Is 23.5 greater than 5? Is 23.5 greater than 5? Are all expected cells greater than 5? So we're good to go. I don't have to worry about anything else. Are all expected cells greater than 5? You have to somewhere, in a goodness or a chi-squared test, you always have to write in your expected cells. They have to see them somewhere. And then independence. Are the events independent of each other? I would assume that we have independence. You're independent from somebody else. You know what I mean? It should be independent. However, what if I have a pair of twins? Do we have independent events? No, because they're going to come in at the same time, at the same birthday, right? So just in case, let's go ahead and just test the 10n. I'm going to do it above here. Is 10 times 94 less than the population of Rosemount high school students? Yeah, we have 22,000, right? So 940 is less than the population. We're okay there too, just to make sure. Everybody with me so far? I can move on. Now we got to do the equation. Expected, or chi-squared, is equal to the summation of the observed minus the expected squared over the expected. So let's go back. Let me double this up so you can see it real quick. What was my first observed data? Q1, but it's 19, right? What was the expected for quarter 1? 23.5. Squared divided by the expected of 23.5. Now what happens is people mix these up. It's always observed minus expected. Don't forget to square it. People will forget to square it. Plus the next one. We're dealing with these two numbers, right? So I'm going to go back here and do 28 minus the 23.5 squared over the 23.5. Plus, I'm going to go back to full screen here. Plus, what was our next number?
16.
Thank you. 16 minus 23.5 squared over the 23.5 plus, and what was the last one?
31.
31 minus, we'll go around the board. Minus 23.5 squared over 23.5. Now you'd have to type this into your calculator. Two different ways. I'm going to show you two different ways to do this. Everybody with me up to this point? Because we have to get our chi-squared value. Take out your calculators. Go to Stat, Edit, List 1. And to start, put in our observed data in List 1. So 19, 28, 16, 31. That's our observed data. Put our expected data in List 2. Good. Now let's say they ask you about a specific cell. I'm going to go to list 3, and I have to go through and do the observed minus the expected squared over the expected, right? What is the observed? List 1. So I'm going to put this in parentheses. List 1. What's the expected? Or where is the expected? List 2. Close parentheses and square it. Divided by the expected, which is list 2. Now when I hit enter, it gives me these four numbers. This 0.8617 is the chi-squared value for this. The second 0.8617 is the chi-squared value for the second one. 0.23936 is a chi-squared value for this one, and then this fourth number is a chi-squared value for this one. The bigger your chi-squared value, the more significant your data. Because here's what happens. What happens as these numbers get further apart? Let's say this is 19 and this was 55.5. We observed 19. They said it should be 55.5, right? That would have been a huge gap. And then I go and square it and then divide by the number. That's going to give me a huge number, right? Whereas if these are close, let's say this was 23.5. 23.5 minus 23.5 is 0. That would give me 0. Would you disagree if that was 23.5, that things are different? You'd be like, well, quarter 1 is supposed to be. It is what it's supposed to be. So what happens is the bigger that chi-square value, the bigger these numbers are right here, the more significant we might find. So at the end, you might want to look at these numbers. Sometimes on the chi-squared test or on a test, they might ask you a specific cell. And you can either do observed minus expected squared and do it by hand or do it on your calculator. What I'm interested in is the summation of those four, though, right? So I'm going to go to stat, calc, one variable stats for list 3, because I want the summation of list 3. Hit enter. There's my summation right here. Right there, right? Summation of x is equal to 6.5106. With me? So I know if I go back here that my chi-squared was 6.51. Great, but that doesn't tell me my p-value. All it tells me is my chi-squared if I have all those numbers. So now, if you look at your College Board sheet, the sheets that you could use for the test, they have a chi-squared chart in there. They have it in there for a reason then. Right? And there's a reason why they gave us chi-squared chart. You have this in your table. It should be one of the very last charts that they give you. I don't know, table what in your tech?
It's the last page.
What is table C? F? Well, this is table F, but in your packet, what is it?
Table C.
Okay, in your packet is table C. It's the very last one. So even though I'm going to show you how to do it on the calculator for most of you that have 84s, they still may have you refer back to this. They might come back and say, I'm not giving you any data, but I'm giving you the chi-squared value. And you have to come up with a p-value. What was our degrees of freedom? 3. So I'm looking at that row. Where does 6.51, our chi-squared value, where does 6.51 fall? Between those two numbers? So the only thing I can tell you is that p is less than 0.1 but greater than 0.05. It's somewhere between those two numbers. So now I can go, everybody understand the chart? It's kind of like a T, just dealing with different numbers here. So I can tell you that my p-value is less than 0.1 but greater than 0.05. If you have an 83, or excuse me, an 84, or you borrow one of mine, you have a test of good fit. So go to Stat, Tests, scroll up. You actually have 2 chi-squareds. The first one is Test of Independence. The second one is GOF. People that have an 83, you don't have the GOF. You can't do this via shortcut, although it's not that much of a shortcut because they still have to type the data into the calculator. Okay, so if you go, well, mine only has a chi-squared test, that's because you can't use it yet. On the next scenario, you can, because we'll be dealing with matrices. So I'm going to go up one more. Goodness of fit. I hit enter. Where was my observed data? List 1. Where's my expected data? L2. What was our degrees of freedom?
3.
You have to type that in. Okay, don't assume that they're going to do it for you, which they don't. And then hit calculate. What is our, now I can get, oh, there's our chi-squared value. That matches up with our chi-squared value, right? And what's our p-value? 0.089. I can tell you if you have an 84, I can get specific. Do these two say the same thing? P-value somewhere between 0.05 and 0.1. They come back and somebody with an 84 says p-value is 0.089. So yep, that's what I said. Right? If you have a TI-84 with a test, you can come up with a specific value. Otherwise, you can only come up with an estimate. Either way, what's our conclusion now? At alpha 0.05, we fail to reject or reject? We failed to reject the null, so it's not that part. Can anybody give me what the conclusion would be? Failed to reject the null. Okay? In favor of there being no measurable difference between the quarters in birthdays for students here at Rosemont High School. That would be your conclusion. In favor of the students' birthdays at RHS being divided evenly among the 4 quarters of a year. Does that make sense? So even though you're looking at going 31, what was our expected? 23.5? But 23.5, notice, remember our chi-squared values for quarter 3 and quarter 4 were the same? They're 116, 131. So how are they the same? Because they're the same distance from the expected values, right? This one's negative, this one's positive. But what does a chi-squared value do? What does a chi-squared equation do?
Squares it. So
Squares it, so we're dealing with all positive numbers. That's why we have to square it, so that we're dealing with the positive numbers. So they're actually the same, which is interesting. I've never had that happen. And same thing with quarter 1 and quarter 2. These two just happen to be the exact same distance because of the value that we got. However, as a big picture, can I come back and say, oh, most people are born in quarter 4? No, I don't have evidence. I say they're all about the same. Any questions on that? That would finish that problem before I go on. Okay, what if we got a p-value of 0.0089? Let's just do a what if. What if I get a p-value of 0.0089? We reject the null. Okay? Sam's right. Sam, you want to say it loud so everybody can hear you?
So I said we would reject the null in favor of students' birthdays being divided unevenly among the 4 quarters of the year.
Okay? But you're kind of leaving us hanging. You're very correct. I'm just being picky here, but I have to be picky. Do you understand what I mean? He's kind of leaving us hanging. Here's just conclusion. Alpha 0.05 will fail or will reject the null in favor of the students' birthdays at RHS not being divided evenly among the 4 quarters of the year. My first question would be, okay, great. Which quarter is different? Wouldn't you want to know? Ooh, most people are actually born in the 4th quarter. So what happens is you're leaving us hanging. So then what happens is you would go back to your data. Remember here, I highlighted this when stating your conclusion. Remember to add a description that shows what kind of relationship is present. Where is there a big difference? So you'd go back to your calculator and do stat edit. And you look at list 3, and you'd see which chi-squared value is the biggest. If this was a situation, I go, ooh, these are the 2 biggest, quarter 3 and quarter 4 with 2.39. So I would say we would reject the null in the favor of the quarters not being evenly divided with quarter 3 and quarter 4. Quarter 4 I think has more than normal. Quarter 3 I think has less than average. So you add that one little thing.